Fromme robotics. So a little bit about me first. So I've been a graduate here and I've taken 6 years of technology classes, but I squeezed it into 4 years just because I've doubled up a lot. I've taken almost every class that we have here, other than the advanced like Tech 1 and Tech 3. I am in the Technology Student Association. For my sophomore year, I placed 6th in nationals in technical sketching, and in junior year, I placed 5th in nationals in 3D CAD. I am also the only certified SolidWorks expert in the district as of right now, and I'm a Microsoft Office Master in 2013. Outside of technology, I'm also a National Merit Scholar. I'm a third-degree black belt and an instructor, and in the fall, I will be attending Western Polytechnic Institute to study robotics engineering. So my advisors for this project, my expert advisor is Patrick Martin. He's a software engineer at Sphero. And my support advisors are my parents, Steve and Cheryl Fromme, and Chad Lewis and Christian Frank, who are my rivals. You can see their posters. So I was in senior projects last year, and I need to already preface this year's project by starting with last year. So last year I created a spokeless bike, which I thought was pretty cool. And then, but what I wanted to do for this year is I wanted to go kind of above that. So this was a purely mechanical project. I did not really step out of SolidWorks a single day over the course of it. At the same time, I was taking computer science though, and so I wanted to integrate some of the mechanical with some of the computer science. So I thought to myself, okay, what can I design that I can program? Of course, the answer is robots. So thinking about the kind of robots I can build, I thought, oh, I know, I will make an exoplanet robot. Except there's a lot of those. So that's already been done, cool, over, great. So I thought about what else I could do with it. And so something else that I came across was a small robot called Sphero, which is, if you guys don't know what that is, it's a small spherical robot you can control with your phone, and it rolls around, runs around. So what I wanted to do is I wanted to combine those two together so that I could have a robot that could roll around and walk at the same time, well, not at the same time, but switch between those two parts as I go through. So that's what the project is. To digress a little bit, here's my logo. So it's called, the name of the company is Protean Robotics. It's after the Greek god Proteus, which is the Greek god of change. The colors here are red and blue on the sides. Red is boldness, it kind of gets in your face, gets your attention. Blue is about intelligence, it's kind of the forefront of technology. If you look at logos like Intel, it's blue because that's where technology is moving. And then those two colors combine to create purple, which is also the color of royalty. This small icon is in the upper right-hand corner. The other logo is a little bit too unwieldy to have on like a small icon for everyday use. I thought about using the center images there, except that's an N and an R, not a P and an R, so it doesn't really apply. So here I have a P and an R, but the R is kind of phased out, so it can either be there or it can't. So that's where the P and the R combines, and again, the whole idea of change, because my robot can change. So when I first walked in, I had a plan of what I wanted to do. So my plan was I wanted a robot that could roll, a robot that could walk, and then it also needed to, well, my plan was to have a solid outer shell. I'll explain in a bit why that doesn't work. I also wanted to have it be omnidirectional rolling, so much like Sphero does, it can roll in any direction you want, so you just point in that direction, it can roll, it can turn, it can do all that fun stuff. I also planned for it to have 6 legs. On the other more software side, I plan to have an Arduino controlling the motors, and a Raspberry Pi controlling the Arduino, and then a phone app talking to the Raspberry Pi over Bluetooth to control everything. If that sounds like a lot, it is, and I decided not to do that because it's a lot. So I kind of cut that down. I got rid of the Arduino because there's really no reason why I need 2 computer chips to do what one thing can do. So I just stuck with the Raspberry Pi controlling everything. And I also wanted to code a phone app in a platform called Xamarin for multiple platforms. I decided against that pretty quickly because if I wanted, the 2 main phones are iPhone and Android. But to code on iPhone, no matter what, you need a Mac, and I don't have one. So even if I did code here on Xamarin, it would just be in so I figured I would use Android Studio instead, because then I can just go straight to Android and kind of through. The technology that I planned on using is SolidWorks to design the robot, servos, motors, and electromagnets as the pieces on there. Arduino, which I decided against. Raspberry Pi, which I decided to use. Xamarin, which I decided against. And Bluetooth to control the robot, as well as using a 3D printer to be able to actually produce all the parts I need. So my 5 objectives are to have a robot that can transition between the 2 modes. I wanted to actually create a working prototype. I wanted to make sure that all the electrical components can actually talk to each other. I wanted to program a phone app, and I also wanted to learn SolidWorks simulation. So a lot of my research is into electromechanical design, design of parts. You guys can read. Here is kind of how I went about this research. So everything in blue is sort of what I did, everything in green is what I did, and everything in red is what I cut out. So for red, with the motors, I decided it was really a comparison between motors and stepper motors is what I was doing to get the rolling part. So the only real difference is that on a motor, when you program it, you say, I want it to spin for 2 seconds. Whereas with a stepper motor, you say, I want to spin for 2 revolutions. So that would have been a little bit easier to program. In a bit when you see my robot, I'll explain a little bit why. But it's easier for me to say, I want it to be this far as opposed to for this long. Electromagnets, that would only apply if I had a solid shell, and I'll explain why later. A lot of this is going to be me explaining why later, but once you see it, it will make a ton of sense. Electromagnets is only for that solid shell. Once I decide to move away from that, then it no longer applies. Arduino is in, I already said I wanted to get rid of, didn't make sense. For Bluetooth, I have a Bluetooth connection, however, it's not fully implemented because of time constraints, and that'll move later. And then for SolidWorks simulation, I do want to make a point about that. There is I would consider myself to have learned SolidWorks simulation. However, there is a test, CSWA in SolidWorks simulation, where you need a 70 to pass, and I got a 69 on it. So I didn't quite pass it. However, a lot of it isn't just the SolidWorks, you also have to know statics and finite element analysis. If you don't know what that is, neither do I. So I sort of, in my mind, I kind of passed because I knew all the SolidWorks stuff, but I didn't know any of the other stuff that it tested me on. So I thought that was kind of unfair. That I graded on stuff that I didn't know about. I guess I should have looked into that first. So this is not my robot. This is a breakout of Sphero. And the reason I'm showing you guys this is because it's important to understand why a solid shell wouldn't work in my situation. Because here we have these little wheels that are running against the outside of the shell, and it's completely separate. The shell and the inside brain don't connect at all other than those wheels. So as that moves, the shell moves around it, and it doesn't really matter where the shell is. Well, for mine, since I wanted it to walk, I would need the center to connect to the outside for the legs to be able to move out. So for it to roll, I needed the center not to connect to it. And for it to walk, I needed the center to connect to it. Those can't both be true. So that's where initially I thought was to use electromagnets to connect the center to the outside shell. But then I realized I could just move the shell. So that's what I do. So I kind of bypassed that. You'll see what I mean when I show some pictures that I'm deliberately withholding from you, so I'm just increasing anticipation. All right. So now some of the roadblocks that I encountered, I 3D printed that, but I didn't want to. So some of my parts are really complex in their geometry. So when I go to 3D print them, it starts out printing some of it, and then as soon as it gets slightly offset, it just starts spewing material and creates this rat nest that is completely unusable in any way, shape, or form. So what we ended up doing is one of the settings we use on the 3D printer creates a more solid base, that way it doesn't shift around and it can print more directly onto the part. It wouldn't rat nest, so it took a while, but we did take care of this, and so I did get all my parts 3D printed, but it did take some time to try to figure it out. The other major roadblock that I had is that when I walked into this project, I anticipated it would be half mechanical and half computer science. So I planned first semester mechanical, second semester computer science. but then I learned that there's this thing called electrical engineering that apparently some people like to make a living off of. So I had to figure out how I needed to integrate all the electrical parts so that I could bridge the gap between the mechanical and the computer science. However, I didn't realize that until second semester, so my timeline isn't cut in half here. This is my timeline now, where I have half of it as mechanical and the other half split between computer and electrical. So I ended up needing to do twice as much work second semester as I did first semester. So going more specifically into my timeline, this was my plan for September and October, and for the most part, it went according to plan. So I did my proposal, and then I went online, I figured out all the parts I needed, and I designed them in SolidWorks so I could design around them. For November, I have essentially two systems that I have. I have the spider system and the sphere system. The spider one walks, the sphere one rolls. Initially, I wanted the spider one to be designed first, the one that walks, and the one that rolls designed later. However, the one that rolls was done like really good. So I decided to do that one first. So even though there's not a red and yellow, I really am on time at this point. I just switched the order in the trains. Same thing in December. Here, instead of assembling stuff, I still have to finalize a little bit more of the legs and how they walked, because that did, even though it was faster with the rolling part, the walking part, not the legs, it did take a little bit more time to design than in January. Things started to go a little bit off with the timeline because I was not finished with all the design, so I didn't really stress test the model. I just continued all the designing with support in the middle. That would hold all of the pieces. At first, I didn't really plan for that. I just kind of figured all the parts would float around. But then I realized I needed something to hold them. In February, I was going to start, in this now second semester, I was going to start out on computer science. So I was going to be learning Arduino and Raspberry Pi. However, since I cut Arduino out, I didn't need to learn it. So I was really more focused on Raspberry Pi and then seeing how I could get Bluetooth to connect to it. I planned to do all the robot stuff before I did any sort of Bluetooth connection to it, but I had to solder the servo driver together because it came with like a little board and then the pins separately. And so soldering is basically just taking metal and melting it so that the parts stick together and then the electricity can flow. And so I needed to solder it together before I could actually use it, otherwise I'd have a really shaky connection. So I just started doing some really Bluetooth stuff to start. In March, not even close. I didn't end up going to app development at any point throughout my project because I had to do all of the electrical engineering that I didn't foresee at the front. So I had to do that, which is much more important than getting the application because I can control it from a computer. I just needed to push that back so that app never really got done. Even though I can get a Bluetooth connection, the app never finished. So at this point, I'm now on coding the servos, making sure that I can get everything to work robot-wise, as opposed to most of it. In April, again, not really close. I wasn't programming any of the controls of the robots. I was soldering the circuit board together and then finishing building it before final presentations. I did get a chance to program some controls of the robots, and you can see a little bit if you go back to my program now. So here I have the initial design. It's the sphere. So here's the solid sphere, and here's the open. Again, this wouldn't work because the center and the outside shell need to be completely separate systems. So what I decided to do is open it up and have an open shell design. So positives of this is that I can have all the parts in here pop out in between the spaces. I don't need to have it. I don't need to worry about it moving the shell being attached to the shell. That's why I went with step moves, because then instead of saying I want it to go for 2 seconds, I can say one of my rotations goes from this part over here to center this part over here, so I can make it roll and have a really easy program that can go X amount of distance without the legs running into the sides here. The only downfall about this design, though, is that it does not have omnidirectional rolling. It only rolls in one axis. So here's the central axis going through. There's the stepper motors on that, and that's the only way it rotates is in one direction. Here's now my final design of everything in it, so you can see the legs coming out. And really dark. Here I have the Raspberry Pi sitting up there, batteries on the back, and then I have all of the sitting on the support in the middle. we'll start peeling back some layers. So there goes the Raspberry Pi, there goes the legs, so you can see where they're seated in here. I take the support away. Now you guys can see those are the stepper motors that drives the entire rotation of the robot. And when I bring them all back, it all kind of fits nicely into the sphere. Close up of the leg. Here's the leg in its up position. Here's the leg where it's down. So these big boxes here, 1 and 2, those are microservos. So those are the parts that I control, how, whether it's an up or it's out or anywhere in between. And when I take this away, you can see that I have this cap here. This part was the really complex one that didn't like being 3D printed, resulting in a rat nest. The reason that these are here is that this leg can always stay in this position. No matter how it's rotated, this leg will always stay vertical in that position unless it jumps gears, which it shouldn't. So it's always here. Otherwise, I would need another servo, which is just a bunch of wiring and controls that I want to do. So here, that's where the servo head fits in, and then here the holes for the axis, so that all the gears fit in. So here I have the final build of my robot. If you're asking a really obvious question, why is it red? Because that was the color coded. It's not my favorite color, my favorite was blue. So here we have all of the wiring here. Traveling through, the wiring kind of fits back into these, almost see it. There's like little sections of space that I left to put wires in. You can see the legs here, all 3D printed. These ones were printed on the smaller 3D printer, so they were reinforced with either fiberglass or Kevlar. The reason the outer legs here are reinforced with a different material is because we just loaded it with a different material. Because I reprinted them because my original legs were too short. They wouldn't reach the ground. So all you would see were the legs waving around wildly and nothing would happen. So I had to fix them. And in here we've got the Raspberry Pi. It's connected with Velcro so that I can take it off and put it back in, make sure it all fits. And then that's different. So here's a close-up of the leg. Again, 3D printed. Here's it down, so it does reach below where the robot is, so theoretically it will be able to lift it. It cannot walk though. It cannot walk. And the reason for that is because the entire robot is 4 pounds. That's really heavy. Especially for these micro servos. So what it does is I can almost set it on the thing. It'll almost stand until it falls down to the ground. The fix for that is if I had a larger, like bigger printer or just a bigger 3D printer, then I can print it out at 10% of its current mass, and then it would be much lighter and be able to lift off the ground. So while it cannot physically walk at this point, it is very good. It's a pretty simple fix as soon as I get the 3D printer. Resources, then it'll be able to grow. Here's a close-up of the circuit board. So all right here is a stepper motor driver, so this allows you to control the stepper motors in the center. Same here. Down here is a servo driver, so all the servos plug into it. Now I can control all of them. That way, I don't have to deal with the wires. It's all right there. Soldering. See some first wire here just because it's really very close. Here again is just the final build. Again, just it cannot walk because it is too. So here's some future improvements that I would do. Right now, I consider this to be not even alpha. I consider this pre-alpha just because it is the very first iteration, and that feature is just improvement here. So one of the things I would do is I would use motors instead of stepper motors, despite them being easier to program. Stepper motors just are not as powerful as motors, especially for their size. So I can get a smaller motor that's more powerful that will allow it to roll easier if I use a traditional motor. And just figure out how long it takes to get from point A to point B instead of saying I want to go from point A. I would also 3D print with less density, that way it can pick up itself. I would have 2 batteries instead of the 1. That way I can distribute the weight a little bit better so it's not as heavy to one side. I would also try to make it smaller. That depends on a lot of things, on how small you get the components and that. But that is more far into the future. I'd make it smaller. I would also want to cover up the circuitry in the center so that it's not out of the if this were ever broken markets. I definitely want to cover that up so no kids are dogs and they're lighting and getting electrocuted. And here I would have the shells screwed together instead of, right now, they're just connected with friction. There's a hole on one side and things sticking out to the other side, so they push together, friction holds them together. I would have them screwed together, and I would have the entire shell be injection molded plastic as opposed to 3D printed plastic because it's more solid as opposed to individual strands. It's all one piece of material. All right, so looking back now at project objectives, here's green and red of what did and did not get done. So yellow here is in yellow for working because it doesn't work because they can't walk and they can't roll. However, the legs can't switch from the inside and the inside will spin. So it can theoretically roll and the legs can pop out and go down far enough for it to walk, so it can theoretically walk. The only thing preventing it is the weight of the shell. Red from that didn't get done because of time and constraints. I had 33% more things to do than I thought I did. And in solver simulation, I had light green because while I didn't pass the test, I did was letting you know this is what I was testing on, statics and finite analysis. So here is my bibliography. So for 30 seconds. Do you guys have any questions? Yes.
So you said that
Yes.
And it looks like it was on its side, so
It was on its side for walking. Once the legs retract in, it will naturally fall back to its center position, or it'll be able to roll, and the legs will push it up to where it's walking. What's up? It's true. So when you start with electrical, you initially start with what's called a breadboard. So it's just where you plug wires into this board, and it creates a bunch of easy connections for you. However, it's not very permanent. It's easy for the wires to fall out. So soldering and essentially melting metal onto it to make sure they connect and control electricity. So here I have two stepper motor drivers, and so each of these will control the stepper motor inside. So I need to connect those to the Raspberry Pi, and then in my program I say, okay, these are connected to these pins, and I need them to send this electrical signal for it to be able to run. Same thing on this side. And here, I have soldered this together to keep it more separate. It came with a bunch of separate pins attached to the front. But I have to solder this down that way it would all stay together. And then if I took it out, I could see some things that wouldn't all be falling out. Does that answer your question?
Any other questions?
Yes.
How would you think about making the model durable so when you do like start producing it and selling it, how would it make it more durable so it wouldn't break?
So what I would do is, while I can't cover the entire thing with a solid shell, what I could do is I could take the inside part here, and I could cover that up and make that part waterproof. So the only thing coming out are the legs. And so if I make every individual part waterproof, then I can make it more durable so that there are no wires lying around so that my dog can get into, so that it's completely closed off. But I can't make the entire thing.
All right. Well, thank you.